Hello everyone. Welcome to our seventh this year CATIA Systems Talk. My name is Gitana Strazdowski and our topic today is Mastering the Fundamentals of CATIA 3D Electrical Architecture Solutions. My guest today is Mehdi Hedhili. He is Electrical, Electronics and Fluid R&D Portfolio Senior Manager. During this session, you will discover how 3D architecture is transforming electrical system design, providing a groundbreaking solution to avoid late-stage error discoveries that lead to extensive rework, waste of materials, and extended project timelines. Please note that during and after the presentation, you will be able to ask questions to Mehdi in the chat. So we're ready to start, and Mehdi, the stage is yours, please.
Thank you, Gitana, for the nice introduction. So, hello, everybody. I'm indeed Mehdi Edili. I'm role portfolio manager for all the electrical and fluid roles in CATIA. And I'm here today to talk about the fundamentals of 3D electrical architecture. So, to begin with, let's give you a little word about who I am myself. By training, I'm a mechatronic engineer from the University of Brussels, Belgium. And I joined Dassault Systèmes in 2011. So I have now more than 10 years experience with the electrical roles in CATIA and working with various industries and electrical engineer and designer all over the world. And out of work in my own time, I am a live role player and an amateur video maker. So I'm not complete stranger to YouTube, and I will try today to do that good in a professional manner. So talking about 3D architecture, first, let's ask why we want to do that and the reasons behind this innovation and this new product, new way of working that we are bringing to the market. First of all, anybody who has ever used an electrical device has faced the situation where the cord is just too short to reach the plug. And usually, not a big deal, you fetch an extension cord and it's solved in a matter of minutes. But earlier this year, I had the situation where I was building a new computer and I discovered when I was assembling the last pieces that one of the cables was just not able in the case to reach the power supply. It was on a Sunday, so of course I had to wait on the Monday to find the shop open, go buy the right cable and install and launch the computer. So my whole project was delayed by an entire day just because of this little error. In the industry, with complex systems that are in cars, aircraft, or power plants, this can obviously be way worse. And the consequences of finding those errors late in the process can lead to an extensive rework. You have to go back completely to the beginning of the process, modify the architecture, change everything, the schematics, the detailed installation to get back to the production. And that can lead to cost times because you will lose maybe miss delivery dates, get delays, which are also very costly. And worst case scenario, the production has already started and you end up with electrical harnesses that just don't fit because they are too short, cannot bend correctly, or any kind of incident like that. And please don't smile, that happened to major aircraft constructor, and you have in this case a huge problem and all your production line will be stopped. So how do we plan to solve that? You guessed it, with 3D architecture. Up to now, we often see some 2D topology, sometimes called fish bones, like this example here from automotive, very classic. You have an outline, rough outline of the car, rough positioning of all the components inside it, and the channels that will communicate. So we just know which equipment has to connect with which other one. That's nice and all, but this is lacking a lot of uh, crucial information, the length, the actual position of the equipment, or any other system that can interfere with that one. So by building this collaborative architecture mockup, we will be able to solve this kind of problem and avoid that in different manners. The first thing is that it's collaborative. So we will consider in the same space reservation, electrical, fluid, communication, waveguides, HVAC, whatever system, and we will approach that in a holistic manner, making sure that they don't interfere with each other. The key benefits we expect from using this 3D architecture mockup are to have an accurate design approximation from the beginning, to be used with simulation and analysis, anticipate the installation to make sure that we are ready for certification, respecting safety requirements from the early stage of development, and be able to already compare key performance indicator to do trade-offs and select the right solution the first time. To finish, one important benefit we can have here is that this basic mockup will help us assist and automate the downstream 3D design, and we will see in a minute how we do so. So CATIA 3D Experience is proposing a lot of rules to fulfill this complete process, and the one we are interested in is a cornerstone 3D architect right here in the middle of this process. The concept is actually quite simple. We have a system architecture, very rough, very basic, hardware elements. We know that we need a motor, a pump, a calculator, a lamp, whatever. And we have signals traveling between them. And when I talk signals here, it's high level signals like the uh, audio video, power supply, or flight control. We don't need to know the detail inside. We just need to know which pieces of equipment are exchanging these signals. And this is what we will place in 3D space reservation. Let's go a little deeper in the general concepts that are used in this 3D architecture and see the rules and applications that are now provided for approximately a year in CATIA 3D Experience. We have created two new roles, System 3D Architect with a bunch of apps that are really the generic one, allowing to handle the life cycle, the system finding, and these kind of things. And one main application, which is space reservation. We will see in a minute what we do with that. And the second one is System 3D Routing Engineer that will help us do the path finding the route for the signals inside the systems with the app System 3D Allocation. What we will do with those two roles is first create the collaborative architecture mockup, create space reservation for components, and what we call integration volumes. I will come back to that in a minute. That's what we see in blue on the right side, and create a network of pathways in which to route our signals, flows, waveguides, etc. And in a second time, we will allocate the 2D component, the architecture component, to these volumes to know exactly what will be placed where. And we will be able to route the signals to make sure that there is a path, a correct path, between a source and a destination. So a word about these volumes. There are three types. We have the first one that is pretty straightforward. It's the component volume. I have an equipment, it's a calculator, it's a pump. I need to save some space in my architecture, my system for this component. So I create a volume and I make it big enough to get to host one or several of these pieces of equipment and components. Then we have two other type of volumes, which are a little bit more specific. In the first place, they don't have any components coming from the architecture that should be placed in there. They are in prevision of the need of components to, for example, split a signal. If I have one emitter, one equipment, emitting a signal going to two pieces of equipment, B and C, I will need at some point to split my signal into two, of course. So these derivation volume are designed to do that. This is where we will place the device that will divide the signal in two. The third one is interface volume. That's the kind of space we reserved when we have, for example, a wall between two different zones, and we need to cut the harness in two at that location. So we will define and we will allow spaces for these interfaces anywhere that it's needed in the system, maybe because we cross, as I said, a wall, or because we need to be able to have a removable part, let's say between a seat and the rest of the car. You need to cut because you need to be able to remove or add, change the seat and reconnect to the system. We know that we need to cut at that location, so we place an interface volume that will host the interface between the two. This is about volumes that are aiming to host components. Then we will create a network of pathways that are built with branches and segments. And that is really the network in which we will be able to place the pipes, the wires, the cables, the waveguides. This is using the usual powerful tool of CATIA to create branches, bend them, connect them in a powerful manner. So let's go a little more technical. That's where we will see a little bit how the software look like and what are exactly the features. And we will see how first we build the architecture mockup. And so we create these volumes and these pathways. We have extensive tools to create the volume, allocate the right type, and create every connection that is needed, place them properly in the system. The volumes are completely free. It's basically not rocket science at that point. It's about creating boxes, cubes, cones, spheres, cylinders, you name it, completely free in the creation in the shape of these volumes. And then we will give them the proper type to identify if they will receive a piece of equipment or will have to host derivation devices or interface devices. Of course, in those volumes, we create connection points. That's where we will come and connect the pathways, the network of space reservation to route all the routables of our different systems. And then in another section of the toolbar, we have the creation of the pathways. And here, as I quickly said earlier, we have all the tools that you can find usually in CATIA to bend, change the length, organize, connect, place, or even route along a surface, or with any kind of constraint that are available in the tool to make sure that we have the right space reservation going into the right place. One important part of the pathways is the fact that we are able to apply some classification defined in tables on these pathways to make sure that we put the right type of signals in the right pathway. That allows us to decide if a pathway should be exclusively electrical, exclusively hydraulic, or is forbidden to a certain type of signal, or force a certain type of signal to make sure that segregation are respected, that we don't put a high power supply next to a sensitive communication signal, creating interferences. or that a signal is not going in a danger zone for it, for example. And so when the routing will occur, we make sure that we give the right constraint to select the right path. When all is said and done with these tools, we will have the kind of network we see here. Of course, in the example, it's extremely simple, two component volumes at the end. In green cylinder, we see an interface. That's where we cross a section and we need to cut. And the little yellow spheres represent the derivation volumes through which we will have to go if we need to split the signal. Of course, in a complete system, the intricacy of the network can be way complex, more complex than that. But here is a very short, small example to identify what are the parts available in this process. So when we have that, we have space reservations. We have made sure that for any of our components, we have a dedicated space that could host it. Now, the whole point using the second role is to allocate the component to the right volume and route the signals. So with the allocation assistant, we will have a complete list of all the components that are available in the electrical architecture, the hardware architecture that was made earlier, and we will be able to allocate them to the volume we just created. Again, this is for the pieces of equipment, for the interface and the derivation that will be automated later. But here in a single tool, single view, we have the list of all the components we need to place, and we have the opportunity to select the right volume for them. Then when we go to the routing, and that is where really the strength of the whole concept is, we have a path finding algorithm that will make sure of several things. First, that all the signals that are emitted are reaching their destination. And it will also select the right path to respect segregation, to go through derivations if the signal needs to be split, at least one derivation, and trying to optimize the length of wires by selecting the right derivation, and taking a note that if we cross an interface, we will have to cut the signal there and interrupt the wires at that location. We are also able to link different types of signals in these pathways, as we said earlier. Here we highlighted some example like line IDs for fluids, or architecture signal, high level, or even net group equipotential. So we can route audio video as one signal, or we can divide it already into 3 different electrical signals if you want to be more precise. So we have here some flexibility. As it is a complex matter, we have defined several signal patterns, going from the very simple one of one piece of equipment is emitting, another one is receiving, 1-1, very simple. But also we can handle in this routing N emitters going to P receivers and making sure that it's the derivation is correct, that we go through the right cut, and that every emitter and receiver is getting the signal properly. To do so, we have in the tool the same kind of interface we saw earlier, signal routing assistant, which can seem a little bit intimidating sometimes, but actually it's very simple. We have one column with all the signals that were defined in the 2D architecture, and we will be able to see the signal type, the pattern we just discussed, to which they belong, and to be able to route that into the network. First, we have source destination, and then we can run the path finding algorithm to find the exact way where we need to route these signals. At that point, we have this 3D architecture. We have all the components allocated to spaces. We have a knowledge of the route of the signals, and this is saved. For each signal, we can we can extract the route with the right cut, derivation, source, and destination. And with that, I want to conclude. I want to highlight additional benefits we can get from this 3D architecture. Like, for example, the check of safety rules. We will make sure by design that we don't have environmental hazards, like an equipment that can cause an electrical spark in a fuel zone, or we can avoid routing anything through non-pressurized location zones in an aircraft, flooded zones in a submarine or a boat, or radioactive zones, etc. We will also make sure that if there is a clash between two space reservations, we see it from the beginning. We don't risk, when we go to detailed design, to have some mechanical parts that are in the way of a routed system. We can also perform particular risk analysis. That is something very important in aeronautics. If there is, for example, an incident with a motor and the part is impacting the aircraft, we can simulate that, see what pathways would be destroyed, and make sure that the most important, the most critical signals, like the flight control, for example, will not go in the danger zone and will always be routed safely. We can also perform trade-offs from the architecture, see if the solution we have devised is really the most performant, and make sure that all decisions are the best from the beginning. And for the downstream automation, we are able to use these routes to create electrical schematics and to place the components in an assisted or even automated manner. And from this architecture mockup, when we have all the components defined in an electrical schematics, well, we'll be able to automate the placement of the final part, the detailed part in 3D. We will be able to place automatically in the detailed 3D mockup. So, coming to an end, I would like to highlight and remind everybody of the key takeaways I hope you will get from this presentation. What we are proposing here is to design a multidiscipline, very important, multidiscipline systems architecture in 3D to get an accurate approximation. That's the real goal of the final product, and get it right by design, the first time. Doing so, we will avoid late-stage error discovery. We will make sure that everything was under control from the beginning. We avoid costly rework. We avoid delivery delays. We will be able to test and validate the architecture and the solution that we have decided to go with. And we will be able to simulate the interferences, even estimate weight and cost, and ensure that all the rules, all the requirements for safety, certification, etc., are fulfilled. And finally, this can be used as the input for the 3D detailed design. And so the architecture, all this preliminary preparation work will drive the creation of the detailed design, making sure that we have this digital continuity and that every decision is informed by the previous step. That's it for me. Thank you very much for listening. I'm open to any question, and I hope this was enlightening.
Thanks a lot, Mehdi. It was really interesting to listen and to watch your presentation. Everything was really nice done. Thanks a lot for your efforts and for being here. I have one question, and I will. I have just one question, but that's important to know. How does the solution address the needs of various industries, such as automotive, aerospace, or construction?
So basically, that's the concept is coming from our discussions with aeronautics. So they were the first to express the need of such approach. Now, it can apply to any industry, actually. Having space reservations, that's a very universal concept. And so we can see that it can be applied just like that to probably any industry you want. Now, maybe there are some specifics from other industries that have not been identified yet. But anyway, this is a work in progress. We are continuing to enhance and enrich this solution. And if specific needs arise, we'll take it into consideration. But right now, we think that this solution can only be applied as is to any industry, and it has already shown some good results with aeronautics and MNO at least.
Okay, thanks a lot for your answer. So I think that we are good today. We don't have any other question except thanks for your presentation, and we will have a short summer break, and we will meet in September on September 5th with all the CATIA systems talks. And for now, we are good. Thanks a lot for everyone who were together with us. And you always can watch the replay on MBSC Cyber Systems community or on YouTube. Please share this with your colleagues, contacts, and see you in September. Bye.
Thank you. Bye.